Hello everyone, nice to be here and come down from the hills that I stay in Valpare. Although I'm a product of Marudam, for the past 3 years I've been with a research organization called Nature Conservation Foundation. And we try and engage with bridging the macro narrative of climate change. We only hear of carbon fluxes, glaciers melting, ice caps, with local, much more complex processes of forests, of small areas of land. And this bridge is often highly complicated and specific. For, as Aruna was saying, 4 different tree species, 4 different creatures, depending on those plants. So, bridging the narratives of larger scale changes that we know of temperature changes, and to local level ecosystem processes outside of the human realm. So, pretending like humans don't exist in certain areas, trying to understand these relationships. And so, that is what the growing focus of certain areas of Nature Conservation Foundation's research work is focusing on. So, I would like to share some stories from the Lakshadweep Islands, from Andaman, from the northeast, from the Annamalai hill ranges of the southern Western Ghats, of what effects climate fluxes have and anomalies have on existing forests, and what their responses are, and what resilience these patches may have, and how these dynamics may affect us and them in the future. So, to start off with where life started off, in the oceans, where climate change is the most direct and simple, sort of visually stunning example, is that 2023 is the dark line, and that's miles above all the other years since 1984 of sea surface temperatures, nearly half a degree above 2022, which is the red line, as you see. So, just framing climate change in a context that within the oceans, that it's unprecedented and exponential, and the last big bleaching event coincides with the El Nino cycle, which is sort of Pacific Ocean current changes, which lead to greater temperatures within the Indian Ocean. And in 2016, the Lakshadweep and Andaman Islands witnessed nearly 70% of coral reefs dying within a 2-week span. And this year, we are yet to see what happens in the season, but as you can see, 2016, which is the highest grey line, to 2023 is a huge jump. So what remains in 2024 for forests and oceans is a large question, and it is the framing of a lot of the urgency and impact. So Lakshadweep also has some positive stories, but although there are large-scale bleaching events, some of the corals from 2016 are re-emerging and are showing sort of recolonization of lagoons, especially deeper lagoons, where temperatures do not affect the corals as much. And Lakshadweep corals are found in deeper lagoons in general, so Indian context may be different from other contexts here of the Great Barrier Reef or Europe, where bleaching events are irreversible. Lakshadweep has also tried putting some cages up to prevent turtles from eating seagrass, and which has seen a lot of re-emergence of small fishes in 6 by 6 square foot areas. So the life is still pulsing in these islands, although the future looks extremely dire. The main question that comes up is, yes, we know that there have been climate fluctuations, we know that we keep hearing stories of past climatic events and droughts, but what lies ahead? And we keep hearing news and models about we're going to lose petrol by this time, therefore our industries are going to collapse, water is going to collapse, people are going to be at each other's throats by the next 10 years, 20 years, 40 years. The line keeps shifting. But the foundation of all of this is that there's multiple pathways from here. We know what has happened, we know we have ravaged much of the planet, but we don't know what goes on from here. And most importantly, all of our models are based on what we know. But because of engaging with ecosystems which are highly complicated, what we know is not enough for what will happen, because all systems respond dynamically, as we heard yesterday, that the feedback loops are constantly pushing and pulling. And so future trajectories of climate change are not going to be based on the past, but rather going to be whole new environments, whole new ecologies, whole new challenges for humans as well. And in this context, I think it's fairly well known to all scientists and all modeling people that all models are wrong. It's just a matter of reconciling which model is less wrong. And this may be highly challenging task.
What is the previous graph in this?
So these are socioeconomic pathways resulting in different carbon levels. So the most optimistic scenario being SSP 4 to 5.5 is that we stop all our use of fossil fuels and we all go back to being wonderful communities relying on organic farming and in local scale areas as anarchists would do. The highest line says that we all live in metropolitan cities flying airborne Teslas and there is no poverty left and we are all just basically living in a Elon Musk world. The red line is a split reality where 70% of the population are going to be very well to do in metropolitan areas, but 30% of the masses are still going to be in extremely derelict, poverty stricken areas. It's up to us to decide which is the most realistic based on our own political leanings, our own biases to what we think the world is heading in. So the sea is very clear. When climate change responds, the temperature of the sea changes, the ocean currents changes, but that effect of oceans on land is far more complicated. India relies heavily on the ocean currents for its monsoons, the southwest monsoon. So I'm coming to it. It relies a lot on its monsoons for rainfall, which all terrestrial ecosystems require. And these are just a few of 70 models used in IPCC, and they all have very disparate ideas of what the monsoons are going to look like in the next 100 years. Some predict that the Western Ghats are going to have higher intensity rainfall, some predict we're going to have drought in certain areas. And so what can be taken out is that nobody knows, and that the relationship is non-linear, in the sense that the effects of ocean on land is not as simple as the effects of ocean on coral. And this is because we have climate, but we also have human impacts on soil, on geology, on biota. We have plants able to change their own environments and their own relationships with each other. So we come into community ecology. We come into a larger level network of processes happening. And so climate alone cannot explain much of the future, but is a very important determinant. If there's no water in that area, it doesn't matter what the plants or the humans do. So going by this, some institutions in India have been creating a greening browning index, which is over the last 50 years, which areas have shown increasing natural greening, either ecologically or plantations or agriculture, and which areas have shown more drought. The left-hand side is just a general pattern, but the right-hand side graph is what we should focus on, which is significant greening and browning. So the gray areas, basically not much is happening, but there are pockets of the land which are showing increasing greening, like the deserts and like more arid regions, and some central Indian and peninsular regions which are showing desertification and erosion. So these are more clear indications of how rainfall and climate are directly influencing ecologies within the subcontinent. And sorry for the bad resolution, but this is a process of how well a forest is able to store carbon. We keep hearing that Amazon and Africa and rainforests are the lungs of the planet, where they harvest all the shit that we put out. But recent research has shown from 1990 to 2040 that the Amazon rainforest is declining in its capacity to sequester carbon and is tipping into being a carbon source because of large trees dying, because of logging. So even our romantic notion that the forest will save us, whatever's left, irrespective of what we do to it, is directly being challenged in a very visceral level. Some of the largest forests in the world are becoming carbon sources and are leading to the positive feedback of permafrost, and therefore the cycle starts spinning faster and faster and faster. However, there is still a split reality where some rainforests like the Congo in Africa remain more or less stable with gradual declines over these years. From our research in Andaman and Valpari, this is largely based on the death of large trees. So although large trees only contribute 5 to 7% of the overall tree number, they hold more than 80% of the biomass of forests. So less than 80 trees of 2,000 plants in a given area hold 80% of all the carbon in that area. If these trees decide to end their existence in that particular area, it results in such a skewed response of carbon holding and the microclimate of that area. And this skewed nature is true for all tropical forests. The question then comes, why are large trees dying and not smaller trees? And one thing that we know is large trees are older, they are more resilient to stresses, but they also take longer to respond to new changes because they're used to certain processes, they're used to certain biologies. Younger trees can change and adapt much faster. So these lagged responses may result in trees having inertia to change, and therefore they may have tipping points where they are unable to respond to stresses after a certain threshold, but that may take 10 years for it to show itself. So a drought in 2010 may express itself in 2024 by a whole host of large trees dying, therefore changing the entire balance and equilibrium of the forest from being a storage capacity, a productive capacity, to a rotting, degrading form. And this is depressing in multiple fronts, but the main being that there's not much we can do about it. It's not based on logging, or it's not based on direct interventions, but it's an inevitable response of trees to their drastic environmental conditions. In Valparai, over the last 30 years, we see a 30% decline in biomass due to natural causes. Although the forests have been protected, 30% of the existing above ground carbon of the forests have declined naturally. So in Valparai, the question then became, okay, we have a sense of what's happening in different ecosystems. We are perched in a particular locality 2,000 meters off the ground in a little protected area with small fragments. But we want to understand then what are the specific sort of interrelations between climate and plants. What are the specific drivers of plant ranges, plant responses, and how does this then affect the entire food cycle, the entire ecological cycle. So within the Valparai Plateau, in the southern Western Ghats, Onemai Tiger Reserve, within the southern tip of the peninsula, we conducted a series of surveys over 400 kilometers over the last 3 years, documenting all the trees we would find in different valleys and how large they are, what are their nearest neighbors to get a sense of their relationships, and then used all of this data of more than 6,000 trees that we found in our transects to pair them with specific ranges that are found in the area. Within this plateau, we can see that the plateau is only 24 kilometers across, but we move from 300 meters to 2,800 meters in a matter of 24 kilometers, and we have a series of climatic gradients in this, of temperature, of rainfall, of wind, and so the specific niches are spatially distributed. So we use this as an experiment to understand how climate affects species distributions and how these distributions will change in the future. So what we found is that some species are very broadly distributed. They are found in large areas of land. Their density is sort of homogeneous throughout the landscape. And this is because they have very broad preferences. They like multiple different landscape types. Here you can see multiple environmental variables, and this is the window in which the species are found. So for example, in precipitation of the coldest quarter, this species is found between 100 to 300 mm, but has a threshold where it cannot exist beyond that point. So that is the window of preference for a species, and we call that the species ecological niche or climatic niche. And this also gives a sense of how resilient a species is. The more narrow the preference is, the less likely it will be able to adapt. The more broad the preferences are, the more likely it's able to adapt. For some species, they have a climatically extremely small envelope naturally. Therefore, their ranges are restricted because of their extremely specific preferences. So, for this species, Philanthus anomalianus, it's only found in less than 200 kilometers square within the Valparai Plateau. And as you can make out, the windows of occurrence, for example, precipitation of the coldest quarter, just occurs in a single point. Anything below or above that point, the species refuses to grow or may face severe stress. So then this starts giving us a sense of why certain species are found in certain areas of land, as explorations like Aruna pointed out that certain hills are far more diverse than others, and how sensitive these species will be to future fluxes and ongoing fluxes of change. So we did this for several different types of species, and we found that there is a broad range of ranges, leading from 12,000 kilometers square to 300 kilometers square, from extremely wide adaptability and occurrence across the hills to extremely narrow ranges. And this is a signal that climate, although very complex in its expression, is a very important influence on flora. Um, this then leads us to what environmental variables are most important for trees, and that is precipitation, which is rainfall, and temperature. Precipitation is all of the four bottom on the different types of precipitation. We often hear of how much rainfall happens throughout the year, but that is not really important for ecology. It's about how the rain falls through the year over time. If we get all our rainfall in a matter of 2 weeks, the land is not going to be able to absorb it. We're going to see landslides, floods, as we see. It's about the nature of rainfall distributed over time. And species have very specific preferences to what kind of rainfall they prefer, and then this affects their stress abilities and therefore their survival, as we see by large trees and the declines in general. So generally stating, species prefer a more even spread of rainfall, not concentrated doses. And the most important sort of determinant of species survival, apart from rainfall, is temperature. And temperature being clear temperature thresholds, where most species are not found above a mean average temperature of 25 degrees throughout the year. So keeping all of this in mind, there is the concept of climate refugia. Most forests will show declines. A lot of large trees will die, but there are going to be parts of the landscape which are naturally going to be much more stable, which are not going to have these declines. And these may be able to hold museums of forests. They may be specific valleys, specific hills, or specific regions. So by plotting these environmental relationships of species into the future, into all different types of scenarios, we find in the southern Western Ghats that the lower latitudes are going to show more climate refugia, where they're going to show less fluxes and more museums of past ecological conditions. Species may show reductions into the area or may show expansions into climate refugia, where they almost are running to safe houses. So it's a matter of finding what these valleys are, where the stability exists, and sort of where these ranges where the species migrations may occur. Following the trees will be the birds, will be the insects, will be the mushrooms. So irrespective of what you do, there's going to be some, what do we call it, refugee camps for trees and ecologies.
But how is it that some places will be more refugee than other places?
Because they are going to be more stable in terms of temperature and stable in terms of rainfall. This is true for lower latitude regions, which show less seasonality, and also for higher elevation regions. So regions with higher elevation will have less fluxes over time. And that brings me to the next point, where a lot of the species that we see show retractions into higher elevation areas. So they leave their lower elevation areas because temperatures are going to increase, seasonality is going to increase. So higher elevation zones within hills of India are going to be climate refugia, and within the higher elevation zones, valleys of higher moisture and lower variability through the year are going to be paramount for existence of many species and ecologies. And this is true across all the species that we found. And many species also showed extinctions within the next 10 or 20 years, irrespective of which socio-economic pathway we follow, just based on our past destruction of the landscape. This is primarily due to temperature. Species which rely heavily on temperature, and due to, as we saw, sea surface temperatures rising so exponentially and land surface temperatures, they show complete eradication of their current ranges in relation to climate.
Explain the Dipterocarpus.
So Dipterocarpus bourdilloni is one of the most beautiful trees of southern Western Ghats. It grows nearly 60 meters tall. And it's found in very specific low elevation valleys at the base of mountains, but it prefers low temperatures but high seasonality of rainfall. However, future climates hold high temperatures and high seasonality, and therefore these valleys may not be suitable for the tree any longer. Another dimension is that climate change has been constant since the last glacial millennium, and species ranges have been changing constantly since the last ice age episode. So Dipterocarpus bourdilloni may be a species which has already been in the limit of its range migration capacity. And any further, it's reached a physical barrier where it cannot migrate or move any further. So the clause for all species in regards to climate change is either adapt, migrate, or face extirpation. If you do not have space to adapt in your genome, if you do not have geographic space to migrate, then most likely you are at the risk of extirpation. So assuming climate change is a basis is built on a basis of assumptions. Assuming that time flows in the way that we in NCF or generally we assume it would based on our knowledge of plants, which may not be very well founded, or our knowledge of climate, we see there is a divided future for plants and forests in India, where a bunch of species show dramatic range reductions. The colors represent different socioeconomic pathways. So darker colors represent more Elon Musk societies. Green colors represent more split world, elite, lower economically developed countries. As you can see, Dipterocarpus bouteloni, Cryptocarya reduce across all socioeconomic pathways. But some species show increases where they like new environments and new ecologies. Therefore, we may see a complete change of communities rather than a complete loss of community. So many species may reduce, but some species will increase. Therefore, the forest as we know it may turn into something we may not like, but the wheel keeps migrating into a different state. We call it a different ecological state, different floristic states, where species which we do not know may gain greater prominence, may bring abundances like, for example, rock pigeons in urban settings, is a skew of a certain population which may not be so common in general ecological aspects. So therefore, we can think of forests moving to an alternate floristic state rather than disappearing altogether. So just the graph basically represents a split reality where some species face losses, but some species face gains.
So just provide 1 second. So the Anomalyana, Bodiloni, Malabaricum, Ravi is fine.
Yes.
Well,
Drypetes whitei and Mystica bedomi are species which show dramatic declines. And Bacteria indica, Palacum ravia, and Orofio thompsoni are some species which are showing increases because they prefer high seasonality areas, they prefer high temperatures, which are going to become more common in future climate.
These changes are last next 10, 20 years.
These changes are in the next 10, 20 years, yes.
When you say socio-economic pathways, does it boil down to carbon emissions?
Yes.
And the changes in the climate
Because of carbon.
Not deforestation or change.
Which leads to carbon emission. Deforestation is one of the sources of carbon emission because of, invariably it boils down to that in this lens, as desertification is a source of. But all of this is in the broad scale still. We are pairing local knowledge to large scale patterns. But to look at something more specific is seasonal variations in rainfall. This is in Sirsi, where each year has a rough mean of how much rainfall occurs, but in the specific month of Jan. But there are some variations in how good certain years are and certain years being droughts. And trees track these trends. So this is our data of fruiting and flowering of trees in the anomalies. The red lines indicate the flowering episode. The blue line is the unripe fruits, and the green line is the ripe fruits. So flowers, unripe, ripe. Flowers, unripe, ripe, across 4 years. So trees track the rhythms of rainfall and respond to the rhythms of rainfall. And when rainfall changes, these rhythms start getting pushed and pulled. Some species show extremely specific windows of the month. So for example, Bombax ceiba, a silk cotton, shows that it likes the winter months of low temperatures, where it fruits and flowers in a very short space of time. Some species within our years of study have shown no fruiting at all. So then this can then bring us to form these connections. Are species not fruiting because they're under stress? Are species fruiting too much because they're under stress? Are species like Mesosphaeria or ironwood doing perfectly fine irrespective of what happens in terms of rainfall? So there are multiple rhythms, and these rhythms are following each other. rainfall fluxes, fruiting fluxes, and following the fruiting and flowering are going to be insects, are going to be birds. They're going to follow the same seasonal rhythms. So, however, an important aspect is that trees are responding biologically. They have adapted to these changes. So, let's say climate changes completely. The trees are going to try and sustain their rhythms. Insects are far more variable. Rainfall comes 2 weeks later, fine, I'll sprout 2 weeks later. So this we call a dislocation of rhythms. We are all in sync. Suddenly we start time shifting. The trees fruit 2 months before the insects come out. The insects don't pollinate the trees stop fruiting. And then we start seeing some patterns of trees not being able to pollinate themselves and fruit. So these are sort of ways in which we can bridge the sort of larger trends, larger deaths of trees and ecologies to more local level reproductive processes and ecosystem level processes. Now, coming back to the concept of biological inertia, younger trees are going to be able to change their rhythms much quicker than older trees, and therefore they're able to change their form. They may be more stunted, maybe not fruiting every year, but saving the resources for a good year, or and etc. And so our ongoing research is going to be finding anomaly years and seeing how anomaly years influence fruiting and flowering 6 months later. So in other areas like in the Amazon, we see something called mass flowering, mass fruiting, where based on a previous drought, trees may get a sense that they're going to die in the following year, so will produce as many children as they can. So I think we can consider that climate change is an overall envelope to what's happening. A plant is responding to its own biological sense of its local area, but it's carrying along a series of dependencies, which are the strings on the leaf. It's dragging along insects, pollinators, things that feed on it, people that use it, and each growth or step that it takes is going to influence and change the matrix of relationships that follow it. Large trees dying is going to influence the orchids growing on it, the birds that feed on it, the people that rely on it for its sap and fruits, the soil, the mycorrhizal communications, etc. And therefore, any fluxes in individual trees are going to carry the dependencies with it. Especially in the case of pollinators and people and life forms that directly reside on the trees. So trees are not just living beings that we are morally entitled to protect and understand, but they are structures which connect the entire matrix together. And by understanding specific rhythms, specific stresses that each tree holds, we can start bridging how large-scale droughts, greening, browning trends, large-scale climatic weather events affect natural forests and how well suited they would be to continue offering us essential life sources like water, like subsistence for so many rural communities, etc. And I think lastly, all the models and projections and weather discounts the resilience and adaptability of even a 50-meter tall tree which has lived perhaps for 150 or 250 years, who has perhaps seen multiple different episodes of drought, has seen multiple different fluctuations of human greed, and has managed to sustain itself throughout the process. So we can never underestimate the resilience of natural ecosystems. We just have to start sensitizing ourselves to perhaps acknowledge the fact that such resilience may be facing a cliff point. And the focus, I think, of focusing on depressing tasks or depressing observation for me is to voice out this dance of collapse. It is a visual collapse, an ecological collapse, but to understand it and be sensitized to these changes and to respect then that trees are continuing to reside and have resilience in ongoing depredation is something that gives me respect and hope. And to be honest, even though I have knowledge of Diplocarpus buruni going extinct, if I look at this 50-meter tall tree, I'm like, you're not going anywhere anytime soon. So it's I think a matter of our own perception, our own biases towards climate change. We must understand the risks of climate change, but not overstate them in the context of much more complex organisms. Yeah.